Assalamu alaikum. So the first question I would like to ask myself and I would like to pose to you is, why is quantum physics looking so unusual compared to your mechanics course? Why is this course slightly different? So it's slightly different because in mechanics, you're always seeing macroscopic objects that are large, macroscopic, that you're familiar with in your daily lives. For example, you've seen cars, you've seen wheels, you've seen inclined planes, you've also seen pulleys, belts, aeroplanes, aircrafts, birds, planets, stars. You see all of this in your daily lives. So, and your 12 years of education before coming to the School of Science and Engineering was all about these big systems. So you're used to looking at problems of this kind. Modern physics and quantum physics is going to look slightly different. The reason is that you've never seen an electron in your life, probably. You've never seen a proton in your life. You've never seen a neutron, a photon. You haven't even seen an atom in your life. You might have seen an image from a scanning tunneling microscope which can show individual atoms, but it's very unlikely. So you're not accustomed to dealing with these small, these are not even microscopic objects, these are nanoscopic objects, right? These are sub-nanoscopic objects. The size of a hydrogen atom, which is called the Bohr radius, is about 0.6 angstroms or 0.5 angstroms. So we're not accustomed to looking at small objects, but these big objects are really made up of these small objects. So one idea in science is called reductionism. Reductionism really means that you take a big object and chunk it up into smaller parts. So eventually, if you take a solid object and chunk it up into smaller parts, you'll get down to the level of atoms. So you see large macroscopic objects, they are really made up of small atoms, but you do not see the individual atoms per se, you only see their average behavior because you're looking at a large number of them. So really you're looking at an ensemble of atoms. Ensemble means a large collection of atoms. So you live in a classical world. But really, this classical world is made up of small quantum worlds. The classical world is kind of an average quantum world. So that's why some of the ideas that you find in this course look very unusual. And the kind of approach that we follow in a modern physics or quantum physics class is different from a mechanics class. So it's a kind of departure from your mechanics course. So that's why some students have said to me that they do not understand what's going on because it's a new way of thinking about the universe. So, but I can assure you that if I'm able to communicate the ideas that I have in my mind to you in a kind of reasonable fashion, with time you'll start understanding what the quantum worldview is. So a little bit of more patience is needed. In mechanics, you have one class. You start off with an idea and by the middle of the class you already understand it, and then you start doing applications. It's not going to work like that in a quantum physics class because an idea is going to span over multiple classes, multiple weeks. That's why the first 4 weeks I've devoted to quantum states and quantum dynamics and the big picture of quantum physics. So you start off with at a particular point in time in a day. By the end of that day, you might have not gotten a full picture. It takes some time for the entire idea to get into your bloodstream. So it's a different way of learning here. It's a different pedagogical style. So please be patient a little bit with it. I still invite questions. You can ask questions as profusely as you like, but the whole picture is going to unfold itself in its true majesty in a few classes, in a few sessions. So quantum physics is slightly unusual in that sense. The other thing you might notice is that there's a lot of philosophy in quantum physics because it's so unusual and the ideas are so counterintuitive. It always evokes some kind of philosophical question. We already looked at one question in the previous class about ontology and epistemology. What is perception? What is reality? A student asked this very nice question. So there is always some recourse to the philosophy of science or the philosophy of quantum physics. Alright, so in the first few weeks, what I want to show you is that the quantum worldview is different. And I'm going to give several examples that can help you understand the quantum worldview. So let's start off with our idea of quantum states. This is going to be the second lecture on quantum states. And we'll start looking at how do we represent quantum states. All right, any question before we proceed? My friends, let's settle down. All right, so first of all, we focus our attention on light. Light is made up of photons. We've already seen that. Photons are these small particles, these corpuscles which make up light. These are the quanta of light. Now suppose we've already seen what this object is. I have a beam splitter. So this is my general notation for a beam splitter. And I have two detectors. So I'm going to represent detectors by this D kind of symbol with a wire wiggling out. So I place two detectors on the two sides of the beam splitter. Let's call this detector D1 and let's call this detector D2. Now what the beam splitter does is that when light comes in, suppose some amount of light, it's not quantum light, it's a beam of light coming in from a laser perhaps. It's coming in and hitting the beam splitter. So what the beam splitter does, if it's a perfect ideal beam splitter, it's like a coin. We have a 50% chance of giving you a head and a 50% chance of giving you a tail. So what this beam splitter does is that it kind of transmits half of the light, right? Half of the light is transmitted and the other half is kind of reflected. So some intensity of light I naught comes in, half of it goes to detector D1 and half of it goes to detector D2, right? So it's a kind of a 50-50 beam splitter. It splits the beam into two parts. It's not a perfect mirror. If it were a perfect mirror, all of the light would have gone to D2, but this is a 50-50 beam splitter. All right, you get this? There's nothing quantum about this. So far so good. So the intensity that this detector detects would be half of the original, and both of these detectors are going to give out the same amount of output. What the detector normally does when you work with detectors inside labs, they get optical power. Power is energy per unit time. They get optical power and give out a current proportional to the power. So you measure the current and you can tell what the input optical power is. That's how any detector works. Got it? All right. Now let's suppose this is a totally classical scenario. You have a laser beam, lots and lots of photons are coming in. And you're not in the quantum world. You haven't entered the quantum world as yet. In order to enter the quantum world, which really means that you would like to look at the quantum properties of light, you have to let away with a large number of photons coming in. You would just like to have a single photon striking the beam splitter, which means that you have some medium in between which reduces the intensity of light so much that you end up with just one photon. Now I'll give a homework question is, if I knew the intensity in watts and I knew the color of this laser, how many photons would come out of the laser per unit time? So you can just imagine how strong an attenuation you would need to do to get just one photon at a time. But there are clever ways of doing that, and probably I'll arrange a tour for you to our quantum lab to see how this is done. But anyway, let's move to the quantum world now. The same beam splitter and a photon comes in, right? A single photon comes in. Now it's misleading to draw a photon by a hard sphere, but let's imagine that this is my concept of a photon. So it comes into the beam splitter, and again I have two detectors. Detector number 1, D1, and detector number 2, D2. Now, since I'm talking about a photon, I can talk about quantum states. And when I talk about quantum objects, I need to focus on one kind of property, or which I call a degree of freedom. So what is the degree of freedom that I'm talking about here? It's the path of a photon, whether it's going in a horizontal path or it's going in a vertical path. So my degree of freedom is an answer to the question, which path is the photon taking? That's the kind of property of the photon that I'm focused on for this particular example. So my quantum state tells me about the path of a photon. All right. So let me write this down in English. So nomenclature and semantics becomes really important when you teach quantum physics, by the way. So that's why I'm going to write this down. My quantum state in this problem is the photon path. This is what I'm focused on. I'm not focusing on the polarization, angular momentum, or any other property of the photon. So in this example, quantum state is the photon path. Now let me label the paths. Suppose I label the horizontal path. When a photon takes the horizontal path, I label this as 0, and I put this in this ket sign. So if now the incoming photon is in the state ket 0. All right, it's in the state ket 0, and I label the vertical path as ket 1. My incoming state is in the state ket 0. Now a photon, first of all, you should remember that a photon cannot be split. It can't be split in most cases, right? Which really means, now how do I justify this? A photon carries energy hf, where f is the frequency of the photon, which tells us what the color is. Now it's not possible in a linear system to have one photon coming in and two photons going out, because then the energy conservation means that the energy has to be halved in each photon, otherwise energy will not be conserved. So really consider a photon to be a quantum which is indestructible. That's why we call it a single photon. It cannot be split. All right. Here we have many photons coming in, so half of them go to one side, half of them go to the other side. But now we are focusing our attention on a single photon, and the photon cannot be split in a linear system. There are other exceptions to this, but in the normal world it cannot be split because of energy conservation. You get this point? Now if the photon cannot be split and we have these two detectors and a beam splitter in between, let me use the word probability. What is the probability that D1 clicks? G? Half. 50%? Half. And what's the probability that D2 clicks? Half. And it would never happen that both the detectors click at a time. That would never happen because the photon cannot be split. And that's why this is a 50-50 beam splitter. So one photon comes in, either of these detectors will click in one go. right? So in order to determine these probabilities, you would need to repeat the experiment with a large number of identical photons coming in, all in the state ket 1, ket 0. So that will tell you that the probability is really half. So by doing one toss of a coin, you cannot tell whether it's a fair coin or a balanced coin. In order to really tell that this is a fair coin which has heads and tails on equal footing, you would have to repeat the coin tosses a number of times. So exactly the same thing. This is like a coin tossing experiment. A single photon comes in and either of these detectors clicks. All right. Now what we say is that the probability that the detector D1 clicks is 1/2, and the probability that the detector D2 clicks is 1/2. So far so good. Now what if I kind of do the following? If I didn't have a beam splitter and a photon came in and I still have a 2 detector scheme, so here is detector number 1, D1, here is detector number 2, D2. The input is ket 0, right? And I put this into this measurement system which has 2 detectors orthogonal to one another. In this case, the probability that detector D1 clicks is 1 and the probability that detector D2 clicks is 0. Likewise, the alternative scenario in which my photon is actually vertical in the state ket 1 and I use the same argument, 2 detectors D2 and D1, the probability that detector D1 clicks is now 0 and the probability that detector D2 clicks is 1. So the states ket 0 and ket 1 are kind of orthogonal, right? I can say that ket 0 and ket 1 are orthogonal. So if I input a horizontal photon, I cannot get a click on the vertical detector, which means that the measurement outcome certifies that the incoming photon is in the state ket 0. It certifies, and it happens with 100% probability. If my input photon were in the state ket 1, the measurement outcome certifies, validates that the incoming photon is in the state ket 1 because only the vertical detector has clicked. So in this sense, ket 0 and ket 1 give mutually exclusive outcomes, right? Mutually exclusive outcomes. I hope you understand the word mutually exclusive. If one happens, the other doesn't. Now in quantum mechanics, you would say that the states ket 0 and ket 1 are orthogonal. Because they give mutually exclusive measurement outcomes. All right. Our window to the world is a measurement outcome. We cannot go right on the photon and see where it is traveling. We have to rely on the measurement apparatus. So our window to the world is the measurement. Now the measurement is telling us that ket 0 and ket 1, the 2 quantum states of the same photon, they are mutually exclusive. And a mathematical savvy way of saying this is that they are orthogonal. Got it? Now, have you ever come across this word orthogonal before? Yes. In what context? Angles, waves, sorry? Vectors. So vectors is the general kind of subject where you come across the word orthogonal. So let's come to vectors, because ket states can also be represented as vectors. So if I have two vectors, and I'm living in a two-dimensional plane, and it's a geometric plane, right? So this is two dimensions called the Euclidean plane, two dimensions, a flat plane, and one vector is A, and I put a vector sign on top of it, the other vector is B, and if in this two-dimensional world there's a 90-degree angle between them, we say that the vectors are orthogonal to one another. And there are different ways of writing this. You could write A is orthogonal to B, or is there any other mathematical operation that you can, that the dot product tells you that the two vectors are orthogonal? So this indicates that the vectors are orthogonal, and you can have the dot product in any order you like. Now these vectors, these nice kind of two-dimensional vectors, live in a two-dimensional space. Exactly in the same way, quantum states, an operation analogous to the dot product, can also be defined for quantum states. And the quantum states also live in a space. These vectors live in a two-dimensional space, sometimes called the Euclidean space, geometric, nice. You can have three-dimensional vectors as well in the three-dimensional space. But quantum states also live in a hypothetical abstract space. You need not remember this, but this is called the Hilbert space. But let's focus on something simpler. Let's call it the quantum space. The two quantum states will be orthogonal to one another if we could define a dot product between two quantum states, ket 0 and ket 1. So by the way, do you know that the dot product is sometimes also called the inner product? If you don't, in general text, sometimes some old text, classic text, it's also called the inner product. And it really tells you what is the projection of one vector on the other. So if I were to draw another vector, ket C is not orthogonal to A. So the dot product would be the kind of projection of vector C onto vector A. This length here, A is going to be A dot C. So it's really the how much what's the projection of C on A, right? So if A and C are parallel, the projection is going to be maximum, and when they're orthogonal, the dot product A is going to be null, 0. Alright, so the dot product is also called the inner product. In quantum mechanics, the inner product between two quantum states can also be defined. Now we need a symbol for this. This is a notation, nothing special, it's just a notation. You put a dot in the middle, in the center of the line. A similar notation exists in quantum physics, which is very popular, kind of invented 90 years ago by Dirac, an electrical engineer. So electrical engineers do physics as well. So let me now introduce that kind of. So I would just say I want a function called an inner product. An inner product between two vectors, say ket 0 and ket 1. And this inner product will be 0 because the inner product of ket 0 and ket 1 is 0 because they are orthogonal. Alright, so now the notation that is used is the following. So I write one of the vectors in ket form and the other vector I write its dual. So if this vector exists in a vector space, there is another space called the dual space in which the dual of this vector exists. So now I want to find the inner product between ket 0 and ket 1. I use the notation which is the following. I write the state 1 I just invert this kind of notation, put this greater than sign into a lesser than sign, and this part of this notation is called a bra. This part of the notation is called a ket. So all of this together, this symbol together is called a bracket. In other words, if I have some state, say, now let me use an arbitrary label, some state psi. Psi is a Greek letter, psi, some arbitrary state. This is a ket. This lives in a vector space, the quantum space. Associated with this ket, there is going to be a bra. That bra is denoted by the same label, but you just reverse the sign. And then the inner product between any two vectors is written in this form. Yes?
To be a bracket, do they have to be orthogonal?
No, they could be anything. Could be anything. So I'm just giving you an example of orthogonal vectors, and I'll generalize this. So this is the inner product between ket 1 and ket 0, like a quantum analog of a dot product. Let me just finish, I'll come to your questions. And this inner product is 0 if the two vectors are orthogonal, and ket 0 and ket 1 are indeed orthogonal, so the inner product is 0. And it doesn't matter which order do I write for these quantum states. I could write bra 1 ket 0. For orthogonal vectors, this is going to be true. What do you mean? Yeah, it's the same thing. So the order doesn't matter. Oh, sorry. All right. Questions? Yes, please.
Could you explain the dual thing?
What does it mean?
Yeah.
So, quantum states live in a space, the Hilbert space, and the space is called and all the quantum states kind of belong to that Hilbert space. Now, if you would like to find the dual of a vector, it belongs to another space because it has different properties, and I will exemplify this when I talk about representing these kets and bras in columns and rows. So please kind of try to be slightly more patient with this. I'll answer this. Yes, please.
Is there any situation where you use a bra over a cat or a cat over a bra, or is this just not?
What do you mean? Like something like this? Of this kind? First bra, then cat?
Yeah, like do they serve any different purpose?
This versus this? Oh yes, this is a totally different object. It's an operator. This is called an outer product. Slightly more advanced stuff, but this exists as well. But this is just a notation for an inner product. And this notation might look clumsy at the moment. It might look kind of strange, clumsy, unnecessary, unwieldy. But trust me, this notation is so powerful that it gives meaning to quantum physics. And it makes quantum physics really easy, as we will soon discover. You'll fully recognize its power when you take the first course in quantum mechanics. Any more questions? Yes, please? It does not. In fact, when you take the inner product, it never matters. It only matters in one subtle way when we talk about complex numbers. All right, so this is an example of orthogonal states. So orthogonal states, two states will be orthogonal when their inner product is 0. So what would this situation be like? The inner product of a state with itself. This is going to be equal to 1 because the projection of a quantum state on itself is 1 because the quantum state is itself. What does it physically mean in the beam splitter example? It means this scenario. you input ket 0 and you look at the probability that detector D1 clicks, you will always get the horizontal detector to fire, always, with certainty. And this is related to this physical scenario as well. So an inner product of ket 0 with itself as well as ket 1 with itself is 1. Alright. Likewise, if I were to take any state psi, which could be ket 0, could be ket 1, or could be in a superposition, as I will explain in a minute, the inner product of any state with itself must also be equal to 1, which is kind of the quantum analog of writing the inner product of a vector with itself is really a mod square, correct? In quantum physics this is 1. I will explain why. Why is it 1? Alright, so it has to do with probabilities, so the inner product is important. Any questions? Yes, please.
Can you please just explain once again that why are we taking the inner product of two same states?
Why are we doing that? Well, we can take inner product of any states, any two states. We can take an inner product of state with itself as well. So why do you ever come up with a scenario of taking an inner product? So it's just the kind of same argument here. And the inner product of state with itself is important. I'll explain when we talk about probabilities. Alright, so now let's come back to our example from the Euclidean space. I'm going to introduce this, generalize this concept a bit more, looking at examples from the flat space, the real space that we are accustomed to. Yes, please.
Up until this point, the cats behaving like vectors.
Yes. And bras are also behaving like vectors, but their kind of orientation changes. I'll explain that. All right. So let's get back to our kind of flat space. Have you ever looked at components of vectors? Yes, you have. And you've talked about unit vectors as well. So now in the two-dimensional space, what notation do you prefer for unit vectors? Ij. All right. So let's stick to something you've already used. So let's call this the I direction and let's call this the J direction. I, by the way, do not like this notation because I also means something else. But let's stick to what you already know. In fact, I'm just thinking whether I should use I or not, or probably you'll get it. Oh, let's use Ex Ey. You're accustomed to Ex Ey as well. So okay, let's use that. So Ex is a vector that points along the horizontal, and Ey is a vector, a unit vector that points along the vertical. Now if I were to take a vector, an arbitrary vector in this space, I can resolve this vector into these basis vectors. These are basis vectors, correct? So that's my first usage of the word basis. So I can, let's suppose this vector is a vector. Now a vector will have some projection on this axis. Let's call this A, and let's call this B, and let's call the name of the vector V. Let's symbolize the vector with V. Now V, when resolved into the two basis vectors, can be decomposed in component form. What will its expression be? V equals, anyone at the back? So let me pinpoint someone. Can you, my friend, yes, can you please decompose this vector V into the two projections, please? From, yeah, let आप बताओ. ठीक है? Sorry? No, I'm not asking about the length of this vector. What I'm asking is, can I resolve this vector into this component plus this component? So, can I do that? Yes, please. So, a plus b, that's it. I can write, I walk along the x direction, along the ex direction a units. So I write a units along the ex direction, and then I end up here, and then I move vertically upward. So I add to this b ay. Oh, sorry, ey. This is my decomposition of a vector. And what basis? I have decomposed the vector into a basis, correct? Now what is my basis? My basis is the pair of vectors ex and ey. So my basis here in this example is the combination of ex and ey. This pair of vectors forms my basis. So any vector in these two dimensions of any length, any orientation, left, right, up, down, can always be written in this form. And what merely changes are these coefficients a and b, correct? Now what is the nature of a and b? What kind of numbers are they? They are scalars. They don't have directions. A and b are scalars because it's just projections. But are they natural numbers, whole numbers, integers? They are real numbers. Could be positive, could be negative, anything. So a and b are real numbers. All right. Generally you could write a and b belong to the real space. Okay, they're real numbers. This is how you decompose a vector in flat space into two basis vectors. You first define a basis. Your basis could be anything, by the way. Any two non-orthogonal vectors could form your basis. I could have chosen a world in which my basis were actually, one of the vectors would be e1, the other would be e2, right? I can choose any basis I like, correct? So there is some arbitrariness in the choice of the basis. All right. Yes, please.
The bases need to be orthogonal.
Not necessary. But for a unique decomposition, they need to be orthogonal. All right. Now let's move back to the quantum world. We're constantly shuttling between our classical notions of vector analysis and the quantum world because it makes our life easier, because it's already good to build upon what we already know. Now in the quantum world, we do not have kets, we do not have these vectors, but we have quantum vectors which are called kets or quantum states. Now any vector psi, now this is a general kind of notation that is commonly used. Any vector, quantum state, this is a quantum state, a ket. Quantum state, ket are synonymous. They are synonymous, means they mean the same thing. Now any in this world that we've seen with the beam splitters, any quantum state can be decomposed into two basis quantum states, two basis quantum vectors, two basis kets. One of them is ket 0, the other is ket 1, and I can write an arbitrary quantum state as ket 0 plus ket 1, because these two are the basis quantum states, the basis vectors, the basis kets for this two-dimensional quantum space. And I need to put some coefficients. Let's call these coefficients A and B. So this is the general quantum state that you can write for this system in which we are looking at the path of a photon, horizontal or vertical. All right. Now these are two basis states, just two basis states, ket 0 and ket 1. Any quantum state can be composed in this fashion. For this particular quantum state, ket 0, A is 1, B is 0. For this particular state, ket 1, A is 0 and B is 1. And you could have things in between as well, and those are called superpositions. Yeah, let me finish. So this is the general kind of form of a quantum state. And since the basis has only two vectors, ket 0 and ket 1, we call it a two-level quantum system. Two-level quantum system or two basis quantum system, because the basis just is spanned by two vectors, ket 0 and ket 1. So it's called a two-dimensional system as well. Two-dimensional quantum system, that's one way of labeling this. It's also called a two-level quantum system, and it's also called a qubit, the quantum bit. But there is one stark difference between the coefficients A, B in the classical Euclidean space and the quantum space. And the difference lies in the fact that over years and years of calculation and wisdom, we've recognized that these coefficients A and B can now be complex numbers. Each one of them can be a complex number. So A and B, each one of them can now be a complex number. So they belong to the complex space. So I give you 2 minutes of silence to let this creep in, and then I'll take questions. Just 2 minutes for you to think about. Yes, please.
Real numbers count होते हैं?
Real numbers भी complex number ही हैं, with the zero imaginary part. So just think about this, and we'll look at the meaning of this. All right, we're going to have a 10-minute break later, but just give 5-6 more minutes to this class before we break for break. Your question? The question here? Yes.
Sir, what I've
ऊंची बोलना.
sir, I was asking that the coefficients of this formula are they representing probability?
They're related to probability, not exactly probability.
Is the square of these?
Yes, but modulus square. I'll come to this. Yes, please.
Two-level or two-basis quantum system is one that has ket 1 and ket 2 as its basis quantum states.
Any two orthogonal states.
Only two.
Yeah, any two. But zeros and ones are labels. You can call them 1, 2, you can call them 100, 200. It's your choice. Any more questions? Yes, please.
क्वांटम के अंदर तो यार कैट 0 होता है या कैट 1 होता है, तो इस साइकिल पर हम हमेशा या 0 लिखते होंगे या 1 लिखते होंगे.
No. It could be arbitrary. That's what a superposition means. Yes.
This is also true for bras.
This is also true for bras. But yeah. Yes, please.
सर हमारी जो जनरल नोटेशन होती है कि 0 क्या है 1 क्या है, is it just कि 0 is undeviated, 1 is deviated?
So the label zeros and ones are our choice, right? That's why I use the word labels. This is my choice. I could call them anything, up, down, left, right. I could call them anything. It's conventional to use zeros and ones because of computing, because of our kind of hang up with computing, right? Because it uses Boolean. We could call that ket 1, ket 2, anything you like. All right, so let's move on. So what do these coefficients mean? Okay, let me go on and then I'll take it. What do these coefficients really mean? So that's what we want to explore. First of all, A is a complex number, B is a complex number, which means that each one of these coefficients, say, can have a real part and an imaginary part. So this A could have a real part, let's call it alpha 1 plus iota beta 1. So it can have real part and an imaginary part. All right. Likewise, this coefficient here can also have a real part and an imaginary part. Now each one of these numbers can also be purely real. It can also be purely imaginary. All right, but generally The general thing is that A is a complex number and B is a complex number generally. But you can have special cases. For example, in the top example, A is 1. It's a real number and B were 0. But A, if A were iota, would get the same result. But let's come to that later. So each one of these numbers is kind of complex. It is complex. So now let's look at our definition of inner product and apply it to this quantum state. If I take this arbitrary quantum state, now when I write psi, ket psi, it could refer to any degree of freedom. So this is general stuff, generic. And then you could map it to different physical scenarios in which map it to different kinds of degrees of freedom. But this is general stuff. Now this quantum state ket psi, if I were to take the inner product of this state with ket 0, this is what it's going to look like. Correct? The inner product of ket 0 and ket psi is going to look like this in our notation. I construct a bracket out of it. Now let's calculate this inner product. Right? You seem slightly worried. Is it okay? Now I'm going to calculate this. Now how do I calculate this? Very simple. Everything, remember, is linear. Right? So if I were to take, just using your example from vector calculus, if I were to take vector A and form its dot product with the sum of two vectors, since it's linear algebra, I could just take the dot product one by one. So the inner product is kind of distributive. So here things are also distributive. So what I do here is I write the bra 0, and now I take this expression, this general expression for the quantum state psi, A ket 0 plus B ket 1, all right, and then I kind of work this out. Now A is a scalar, right? So it can move around. So this is, so if I put a scalar here, alpha, so I can put alpha here, or I could put it here, doesn't matter, it's a scalar. Brackets are permeable to scalars, okay, they can move around. So this number A, I can write here, this bra 0, ket 0, plus this scalar B, bra 0, ket 1. So this is just opening up the distributive law, the linear law. Now we know that, already know that the inner product of a legitimate quantum state with itself is 1, and this is 0, because ket 0 and ket 1 are orthogonal. Hence the answer to this is going to be A. So this coefficient A, what is A? A is the projection of the quantum state on one of the basis vectors. Just like this length is the projection of this vector on one of the basis vectors. Likewise, the other coefficient will be the projection of this vector on to the orthogonal basis. So I get this term is the projection of psi onto ket 0, or the inner product of psi with 0. Likewise, B, I can just write it straight away, and you can also test this out. B is going to be the projection of psi, or the inner product of psi with the other orthogonal state. So the coefficients, which are, and by the way, A and B can be complex numbers, unlike your real case. unlike your 2D Cartesian space in which the projections have to be kind of measurable lengths. Here, still the physical reality of these coefficients is unknown to us, but at least we have some kind of mathematical motivation as to what these coefficients are. These coefficients have a special name, and I'll explain after the break why they have this name. The special name for these coefficients is that these are called probability amplitudes. Alright, so let's take a 10-minute break and then we'll start off with your questions and move on. Alright, so let's begin with a couple of questions. Yes, please. No, but you can have superposition as well. I'm going to explain that. Any more questions? All right. Yes, please.
I'm kind of confused as to how this inner product connects the two states. Like, what does it do?
What does it do to let's see. So let's look at the meaning of the probability amplitudes, and then we'll see what this inner product really means. So what are the probability amplitudes or the coefficients A and B? Now suppose if I were to say that no one really knows what are the probability amplitudes, what is their physical meaning, it might not be a very misplaced statement. Because the probability amplitudes themselves, they are really important, but giving a meaning to the probability amplitudes in the language of English, in any language that we are accustomed to as human beings, might be slightly tricky. In fact, in most cases, it's very hard to determine easily what A and B would be for a physical state. However, if I were to do something else, I can attach a meaning to some function, some other property of A and B. So let me explain this. So if I were to take the quantum state psi, whose general form of course is A ket 0 plus B ket 1, I've already seen that if I were to take the inner product of this state with ket 0, which means I construct this bracket, we've already done this, what's the answer? Small a. This scalar, this complex number A pops out. But what is the meaning of this A? It's easy to say that A is the projection of the quantum state on this basis quantum vector. But what does it physically mean? In fact, it's very hard to define a physical meaning to A. However, if I were to take this probability amplitude A and multiply this scalar number with its own complex conjugate. Does everyone know what a conjugate of a complex number is? Yes. Right. If I were to do this, are there any no's who don't know what a complex conjugate is? Alright, okay. So do you know what a complex number is? So in our first class we encountered complex numbers. Suppose I have a complex number 3 plus 2 iota. This is a complex number, correct? if I were to find the complex conjugate of this complex number, I put a star on top of it as an aesthetic. I would keep the real part as it is, but I would invert the sign of the imaginary part. That's what a complex conjugate is. All right. And if I were to multiply the complex conjugate of a scalar with the scalar itself, the answer will be real. All right. And the answer can also be represented as A modulus square. And why is that? Can we give a few homework problems on complex numbers, please, about what is modulus square and all? So this is how we define a complex conjugate of a scalar. Got it? Now if I were to take this probability amplitude A and multiplied it with its complex conjugate in either order doesn't matter because these are scalars. This is also represented as A modulus squared. Then this is some kind of probability of measuring something. Now what is it? What is that something? So the probability amplitudes do not have kind of easy amenable meaning of their own, but their modulus square have a meaning. Their modulus square is some kind of probability. So the numbers, the complex coefficients themselves are some kind of proportional to the square roots of probabilities. All right, so these complex numbers, if you were to take one of them and find the modulus square of each one of them, that is going to be equal to some kind of probability. All right, so now let's see how this unfolds in our kind of photon example. So in this case, let's consider this case first. Let's redraw this. Two detectors, D1, D2. A photon coming in, the quantum state of the photon is ket 0. So this is my quantum state. The probability that my horizontal detector clicks, which is kind of the probability that I get the label 0, because this corresponds to the horizontal detector. So let's call it 0, and let's call the vertical detector the outcome. Let's call this, if this detector clicks, let's say that my input state would get 0. So the probability that this detector clicks is going to be given by the input state ket 0 and its projection onto ket 0, right? Modulus squared, and this equals 1. My probability in this example of making this detector fire, which is the ket 1 detector, is my input state, which is still ket 0, and I want to find its projection onto ket 1. So, and then I take the modulus square of this bracket, this inner product. This is going to be equal to 0. Yes, please.
When you inner product with 0, 0, it was 1 earlier, then you square that.
It's 1 square of 1 is 1. And it happens that these are kind of real numbers, but they can be complex as well. So likewise, if my input were ket 1, this would be 0, this would be 1. I don't want to draw this. So now I'm attaching physical meanings. This is totally generic. This is mathematical. I'm attaching a physical kind of example to this meaning. So the probability amplitude when modulus squared gives some kind of probability. Now let's look at the other example in which I have a beam splitter in between. I have this beam splitter. A photon comes into the state ket 0. And I have two detectors. All right. Now what happens is single photon, we've already seen that this probability is half and this probability is half. Probability is something you measure in an experiment. It's a measurable outcome. Now what does this beam splitter do to the quantum state? It must do something differently than this scenario, because otherwise you could have the probability here would be 1 and 0 here, or vice versa, but that's not the case. The probability here now is 1/2 and the probability here is now 1/2 here as well. So this beam splitter does something to the quantum states. What it does is that it creates a superposition. Now the beam splitter, now when you have a computer, you have input states and then you have kind of logic gates, which kind of square things, which kind of take ORs, ANDs, NANDs, different kinds of transformations on states. That's what computing means. So this beam splitter is like, it does some transformation on a quantum state. What this beam splitter does, one possibility is that this beam splitter takes in an input ket 0 and it produces a new state, or it transforms the input state into something else. Now I'm proposing that what it does is the following. It takes this input state, and the action of the beam splitter on this state is one of transformation, is that it creates a superposition of ket 0 and ket 1. It creates a new quantum state. But every kind of quantum state must have some coefficients as well. So I propose that the coefficients are 1 over under root 2 here and 1 over under root 2 here. So what this beam splitter has done really is that it has taken an input quantum state and created a superposition out of it, transformed it. It's kind of a logic gate that creates a transformation, and this state cannot exist classically. What this means is that really, if you don't look at it, the photon is now in a superposition of both of these paths. All right. Now, what's so special about these coefficients? Now let's take this quantum state, this one. Let's call it ket phi. All right. Ket phi. I can give any label to a state. Let's call it ket phi. So the beam splitter has taken an input ket 0 and produced a new state ket phi. Ket phi. Now this ket phi is being measured. How are we measuring ket phi? We have two detectors in two kind of orthogonal directions, and we're trying to look at the probability that each detector clicks. So now our input state that is going into the measurement apparatus is ket phi. So what, are you getting this? So what is happening now is that we would like to find out the probability that this detector clicks, D1 clicks. The probability that D1 clicks is going to be, what is it going to be? It's going to be equal to, how do I compute it? I take my state ket phi, find its overlap with ket 0. I construct this bracket and take the modulus square of it. Now what is the bracket? What is the value of the bracket? If I were to take this state and project it onto ket 0, what will my result be? 1 over under root 2. 1 over under root 2. Then I take the modulus square. So I get 1 over under root 2 modulus square, I get half. And this is my desired result. So what the beam splitter could have done, and we'll show that it does exactly this, is that it has taken an input state and created a superposition. This superposition wouldn't exist classically. Alright? And there is also some finite probability that this detector clicks. So what's the probability that D2 clicks? It's going to be ket phi overlap with ket 1, which is the ket 1 detector, which is a vertical detector. And I take the modulus square, I still get 1/2. Alright? And what is the sum of these probabilities? 1. So there has to be some constraint on the two amplitudes, on the two probability amplitudes, so that the sum of their modulus squares is 1. Right? Otherwise the probabilities will not add up to 1, which is unphysical. Luckily, physics respects probabilities. So the general quantum state psi can be written as A ket 0 plus B ket 1, where A and B are both complex numbers, can both be complex numbers, and A modulus square plus B modulus square equals 1. Right. So the coefficients A and B, they call probability amplitudes. They may not have a meaning of their own generally, sometimes they do, and they are such that their modulus square means something. Their modulus square means probability in a certain measurement experiment. The sum of those probabilities must always add up to 1. Now it's possible that, suppose, let me give you an example. Suppose the beam splitter does not produce this superposition. Rather, the beam splitter produced 1 over under root 2 ket 0 plus iota 1 over under root 2 ket 1. First of all, is this a valid quantum state according to this prescription? No or yes? So what's A here? A is 1 over under root 2. The modulus square is of this amplitude is 1/2. What's the modulus square of this? Minus 1/2. Can you take this number and please on your notebooks, this is B, this is our B here. Can you please write down the modulus square of this number, and I'll walk through and see if you can figure it out. करके देखो.
What exactly is this last state which you written?
The last state?
Yeah.
I'm just asking whether this is a valid state. Can the beam splitter produce this? Sorry, ket 0 or 0? Ket 0. Yes, that's just a horizontal input.
But what if the answer of this is 0?
The last question that I've asked. well, that means that the object does not exist.
Question. So we get 1 by 2 through this whole working, right? All of
Yes.
this legitimate.
So what's the modulus square of the second probability amplitude? 1/2 or minus 1/2? It's 1/2. The modulus square of a complex number is always real. So look at our definitions. I take the complex conjugate of this, which is minus 1 over under root 2, and multiply it with the number itself. It's 1/2. So it's possible that the beam splitter has produced this state. Again, it qualifies as a true legitimate quantum state. Why do I say legitimate quantum state? Because the sum of probabilities must add up to 1. It's impossible that if you are kind of doing this experiment, one of the detector must click. It's not possible that, first of all, why can't both detectors click? Because photons cannot be split. Is it possible that neither of the detectors clicks? Well, in an ideal world, it's impossible, because the photon has to go somewhere unless it is annihilated by some other absorbing material, or the detector fails to kind of detect it. There are experimental imperfections always. That's okay. So in a real ideal world, in a real quantum world, the sum of these probabilities must add up to 1. The complex coefficients do not have a meaning of their own. However, their modulus square does. Their modulus square is a probability. And how do we know that this is a probability? This is the genius of another physicist, Max Born. And it's generally called the Born's postulate. It's very hard to derive this from first principle, but this is how it is. Now let me give you, so if this is true, we can also write quantum states of this kind. For example, I can have a quantum state of this kind. Is this a legitimate quantum state? I mean, generally. This is also a legitimate quantum state. Here I have a complex number. Is this complex? Yes. Every real, every imaginary is a complex number. And all of this is also a complex number. And now this has both a real and an imaginary part. Right? And if I take the modulus square of this, which is 1 over 3, the modulus square of this is going to be 2 over 3, because the complex conjugate of this is e raised to minus I phi, and the e minus I phi kind of cancels out the e I phi. I'm left with 2 over 3. So this is a legitimate quantum state. And another way of saying that the sum of the probabilities adds up to 1, another way of saying this is the following. If I were to take any quantum state and find its inner product with itself, the modulus square of this number must be equal to 1. Can you prove this, please? I give you 5 minutes to prove this based on the general form that we have for a quantum state. Please prove this. इसको पहले करो, फिर आपके सवाल का जवाब दूंगा. In order to kind of show that this is true, you need to also understand one more thing. If I have I know what a ket is. I now need to know what is a bra. So if this is my ket, I need to have some recipe for constructing the bra for it. And the recipe is the following. If this were my ket, I take all the kets and convert them to bras. So my bra psi, which is the dual quantum state, the dual vector for this quantum state, I just write bra 0 plus bra 1, and I take these complex numbers and write down the complex conjugates of these numbers. So this is my bra psi. Alright, so this is the rule. Now this is a rule. So I'm now moving to a kind of dual space, and the dual to this vector looks like this. Now just take this for granted until I introduce row and column vectors, but let's take this for granted for now. Now I construct this bracket. So I can write down the bra, I can decompose the bra in the following fashion: A star bra 0 plus B star bra 1. This is my bra, and the ket is A 0 plus B ket 1. Now if I were to use my orthogonality kind of arguments, this will give a non-zero product and this will give a non-zero inner product. Other terms will turn out to be 0. So this will come out as A star A plus B star B, but this is A mod square plus B mod square, but this must be 1. So the inner product, and if I take the modular square of both sides, it's going to be 1. So the inner product of a legitimate quantum state with itself, modular squared, gives me 1. And why do I call it legitimate? Legitimate means allowed, permissible, because the probabilities must always add up to 1, right? There's nothing that goes missing in the process. So in order to conserve the probabilities, every legitimate quantum state must be in this form, and if it is in this form, it's called, the state is called to be normalized. It's just like saying when you compute probabilities, in the denominator generally you add up all the probabilities to normalize your answers. So quantum states must be normalized. So if one of the coefficients is unknown and you're just given with one coefficient, you can use the normalization property to determine the other coefficient. You can give this as a homework problem. Alright, so before we move on with some interesting physical manifestations of the superposition, any questions? Yes, please.
Was the gravitation and the expression for superposition, were these based to fit experimental results?
Yes.
Or were
Yes, please. Open up, speak up, please.
So when you kind of find a state and you that will be always add any probability.
Like this.
Yeah, like you always have to add A and B, or do they have value?
So they can have specific values as well, but this is the general form. Yes, please.
So were the coefficients in a quantum state allowed to be complex numbers, or were they, discovered to be complex?
Well, the question that my friend has asked, whether these coefficients were allowed to be complex or were they discovered to be complex. So no one discovered these coefficients. So you come up with a mathematical structure that describes experimental outcomes. And the mathematical structure, due to Heisenberg mostly, is based on the fact that these numbers have to be complex. And this kind of linear algebra was known before quantum mechanics as well. It mapped directly to quantum mechanics in a neat fashion. Yes, please.
So far and moving forward, are we going to treat ket 0 and bra 1, etc. as kind of basis vectors?
Yes. So remember, we're talking about qubits, two-level quantum states. Now let's look at one or two physical kind of really neat examples. Suppose I kind of have a beam splitter here. All right. Remember, photon cannot be split. One experiment cannot tell you what the probabilities are. Do you understand this? So you have to repeat multiple number of times to build up the statistics to find out what the probabilities are. By one toss of a coin, for example, you cannot tell what the probabilities are. You have to repeat the experiment in a sequence of identical manners. Okay. Now suppose I have this arrangement in which I put 3 beam splitters back to back, and I have a single photon coming in, just one photon coming in. This kind of it's going to be an experiment which is like a master stroke, very difficult to build. But suppose these 3 beam splitters are put in tandem, one after the other, and I have 3 detectors, D1, D2, D3, D4. The same degree of freedom, the path of photon, horizontal versus vertical is my ket 0 and ket 1. That's my basis, that's my degree of freedom. I still have a qubit, a 2-level quantum system coming in, because the photon can either be horizontal or vertical or in a superposition thereof, but there are only 2 basis states. Now this photon comes in the horizontal state. Now you can just speak up, what's the probability that D1 clicks? 1/2, because here a superposition is created and the projection onto this state is going to be 1/2. Projection modulus square is 1/2. What's the probability that this D2 clicks? 1/4, because it's going to be half of this. So half goes probability half, it goes here, and then there's another probability half that it is kind of reflected in this direction. So this is 1/4. What's this probability? 1/8. 1/8. Fine. Okay. So now there is a succession of probabilities. Suppose I call this path 1, 2, 3, 4, 5, 6. Kind of strange. Okay. So the probability, for example, that detector D2 clicks is going to be kind of a cascade of probabilities. The probability that the photon comes in here, probability 2, and you multiply it with the probability that given this path is taken, what's the probability that this path is taken, and that is generally called a conditional probability. So given path 2, what's the probability that the path 3 is taken? Have you studied conditional probabilities? Alright, so if you don't understand, it's fine, but this makes intuitive sense. Even without knowing the Bayes rule, you can kind of determine that this probability is going to be 1/4. Half multiplied by half. It's good? Alright, so this is called the Bayes rule. Anyway, this is simple so far. Now let me construct an experiment which is not hypothetical, which we do all the time in the lab, and which actually exposes and brings to light that really a superposition does exist. So far you might come up with a counter argument that this superposition is just kind of mathematical jugglery. But now I would like to come up with an experimental outcome that we see happen and which can only be explained if this were a superposition that is created by a beam splitter. So this is a very nice simple introduction to quantum physics, really. Quantum states, ket notation, bras, brackets. I think you should be proud if you understand this. This is actually understanding in a physically insightful manner of what the quantum world looks like. I'm now going to talk a little bit about an interferometer, the simplest quantum computer yet that you can build out of this photon polarization degree of freedom. Suppose I have so in order to draw this better, let me first I have a beam splitter here. Sorry, let's change the direction. Beam splitter here. And then I have another beam splitter here. Two beam splitters. And then so I put this in a kind of rectangular arrangement. And at these vertices, I put perfect mirrors, which I'm going to draw with these thick lines. So here is my beam splitter 1. Here is my beam splitter 2. Here is one of the mirrors M1. It's another mirror M2. Perfect mirrors. So a beam splitter is a half perfect mirror. But these are perfect, truly reflecting mirrors, which are fully coated with silver or so on. They reflect all the light that impinges upon them. Now once again, my degree of freedom is the photon path. Horizontal is my ket 0. So I put this at the back of my mind that H I'm labeling as ket 0. Horizontal path I'm labeling as ket 0. Vertical I'm labeling as ket 1. Now each element that I put in the path transforms the quantum state. The beam splitter transforms the quantum state and the mirror transforms the quantum state. Now if I were to put two detectors at the output, so the input photon comes in here, all right, and the output photon goes out here. So this is my input port. My inputs are coming in through this port, right? Every device has an input port and an output port. So this is my input port, and here I have my output port. And so I build this, let's call this a simple quantum computer or an interferometer. And at the output port, my connection with the quantum world is through measurements, is through detectors. So I put two detectors at the two possible output ports. D1 and D2. हाँ जी.
Can I not output on horizontal and one end?
No, I'm just outputting here. This is my system. This is inside a black box, and this is my output port. I can, if you want to play with it, you can put your outputs anywhere, but this is what I'm doing.
But will it not just generally output in M1 and M2, like horizontal?
It cannot go out of the system here. So these mirrors are just to steer the paths of the photons. All right. So now, intuitively, what's the probability that D1 clicks? Half.
So where is the light source?
sorry, the light is coming in here. This is my photon, my incoming photon in the state ket 0. So what's the probability that D1 clicks? Half. What's the probability that D2 clicks? Half, right? So it's just like having two beam splitters in tandem, one after the other. One has a half probability, the other has a half probability. But lo and behold, when we perform this experiment in the laboratory with a single photon, only one of the detector clicks, always. Always. Now you have to believe me in this, and in fact, seeing is believing. You can watch countless experimental verifications that you can find on the internet, or just walk 2 stories above and see what happens in our laboratory. So only one of the detector clicks. Now here you are struck by an experimental observation that cannot be explained classically, and which leads you to think that superpositions exist. Now I'm going to explain it with the kind of formalism that we've learned about is what's going to happen. So what really happens is the following. So let's look at the progression of the state through this quantum computer or interferometer, right? So we want to look at the progression, and for that we need to know what each element does, right? So we already know that what a beam splitter does is the following. A beam splitter takes an input ket 0 and creates a superposition. Suppose it creates a superposition, and that superposition is 1 over under root 2 ket 0 plus 1 over under root 2 ket 1. Suppose this happens at the beam splitter, any beam splitter. But the beam splitter can take 2 possible inputs. It could either take a photon coming in ket state 0 or ket 1. So here this beam splitter can take in a photon coming in the horizontal direction or a photon coming in the vertical direction. So we need to define what it does to the orthogonal state as well, ket 1. Right? You get this point? In order to fully describe what the beam splitter does, we need to describe what it does to either of the 2 orthogonal inputs. One is ket 0, so this is what it does. It creates a superposition, and with the other inputs kind of input state, it creates a superposition, but with the sign changed. So this is how a beam splitter works in physical reality. One possibility that it works in this fashion. All right, this is given. This is the truth table of the beam splitter. So you have truth tables. Are you familiar with truth tables of logic gates? This is the truth table of a beam splitter. This is what a beam splitter does to an input. Now this is the kind of given. Now let's see what happens and what does a mirror do. So if a mirror is input with ket 0, it would create ket 1, right? So if it's input with ket 0, it would create ket 1. If it's input with ket 1, it would create ket 0. All right, so that's what a mirror does. So this is what, so we have identified what each element in this quantum computer does to various kinds of input states. Got it? Now let's look at the progression of the quantum state as it flows through this interferometer. The input is ket 0, so let me move to a blackboard nearby. In fact, you have to be patient. If you understand this experiment, I bet you would understand 90% of quantum physics. This one experiment is all of quantum physics, most of it. Let me finish this, right? So we want to look at the progression of the quantum state through this device. Our input is ket 0. What does the first beam splitter do? It creates a superposition. which state does it create? So it comes in, and now the quantum state is somewhere here, right? It's in a superposition. This is the quantum state that has been created by the first beam sphere. All right, so we've created 1 over under root 2 ket 0 plus ket 1, correct? I've just pulled out the factor out of this, factorized state, okay? Now the quantum state sees two mirrors. Now what we would like to do is, what we're trying to do conceptually at the back of our mind is we're trying to find out what the quantum state looks like in this region after this quantum state. Remember, we're not measuring the quantum state at this point. We're just predicting what it might have done. Because if we were to be over clever and started measuring the quantum state here, things will go topsy-turvy. And we're going to explain this. But now I want to look at what the state might be like after it has seen the mirrors. Right? So now this photon, which is presumably in a superposition, has now been reflected by two mirrors so that the paths change. So after the kind of mirrors M1 and M2, ket 0 will transform to ket 1. A horizontal photon becomes vertical path, the vertical path photon becomes horizontal. So ket 0 becomes ket 1 becomes ket 0. And since it's a superposition, the order doesn't matter. So this I can just write as kind of ket 0 plus ket 1. So this is the state, say here, right here. Now finally the kind of two paths converge. The two components of the superposition, they then reconvene. So it's just like two people taking two different routes. Here is just that we have one person taking two different routes and then recombining. So the two paths recombine. Remember, it's still just one photon, still one photon. The two paths reconvene, and here you would like to find out what is the state after the photon leaves the interferometer, so that we can compute the probabilities at the end. So now I just want to put this over here and see how this thing evolves after the second beam splitter. So 1 over under root 2, remember I have to keep things linear. This ket 0 must transform in this fashion. So I would write ket 0, this thing goes as this. Plus this ket 1 must transform in this fashion. Linearity, the distributive property that we've been talking about, 1 over under root 2 ket 0 minus ket 1. Now I open up the brackets. You will notice that this ket 1 has a negative phase. Let's call it a phase. It has a negative sign associated with it. It just cancels out this term, and I'm left with half ket 0 plus half ket 0, which is ket 0, which means that the photon ideally emerges through this path only, and the probability that detector D1 clicks, since this is ket 0, the overlap of ket 0 with ket 0 is 1, modulo square is 1. This probability D2 is 1 minus this, it's 0. So lo and behold, in this quantum interferometer, or let's not use that word, in this quantum computer, due to the superposition that has existed inside the computer, which we were not privy to, which we did not observe firsthand, the final outcome is only explicable or explainable by proposing that a superposition must have existed. Only this detector clicks. Now you have two random objects, totally random objects, which give a 50% probability of reflection, 50% probability of transmission, and you put them two together and you will see that only transmission is taking place. Right? There's no reflection here. So you put two objects, each one of them has a 50% probability of either reflecting or transmitting, but when you kind of put them in tandem, put them together, only transmission takes place. Now this is really, really strange. Now in the next lecture, I'm going to start off with some explanations of this. Alright, see you on Thursday, inshallah.